Hello and welcome to my lecture review for the Cybex book, the CompTIA Server Plus Study Guide. It is the 2016 edition. It is published by Wiley, and this is going to be covering the individual chapters prepping for the CompTIA Server Plus certification. Alright, so today we're talking Chapter 8, which is about networking. We're going to be looking at the three main objectives for this section, and that is looking at IP addressing, comparing and contrasting ports and protocols, and lastly, we're going to be talking about cabling. That means cabling, implementing proper cabling management, procedures, understanding structured cabling, and things like that. So, there's a certain level of base understanding. I'm assuming that you already understand classful addressing, Class A, Class B, Class C, and things like that. So there are some addresses that are also equally important if you already know classful addressing, like understanding the private ranges of a Class A, B class, an A, B, and C. So, like if you have something that starts with a 10, knowing that that is a private range, meaning not internet routable. Or if you have a Class B and you're in between 172.16 through 172.31, that's also a private range for the Class B network. And for the Class C range, it's going to be anything with the 192.168 network. Those are all private address spaces, meaning you can use them on your internal network and they are not allowed on the internet. You have to have NAT, network address translation, enabled to actually browse the internet with that type of address. So that's private address ranges. We also have a loopback address, and again, that loopback address is really just a clever way to say look back at yourself. For IPv6, that's going to be a : 1. For IPv4, that's a 127.0.0.1. And again, that's just a clever way of saying look back at yourself. What happens if you don't have an address? What happens if DHCP is misconfigured or giving out wrong information? You may get an automatically configured IP private address. An automatic private IP address. APIPA, and a PIPA address. And that is anything that starts with a 169.254, that will be the private address space. So what's the purpose with that? Essentially, if you have a bunch of network devices on a LAN and they cannot receive a IP address, they're all going to use a PIPA address. The nice thing is they can communicate with one another on the LAN, even though they won't be allowed internet access. They can at least still communicate locally. The IPv6 version of that is going to be FE80. And you will notice that IPv6 FE80 is popping up more and more locations. So if you're doing an IP configuration on a Windows machine, you should notice that if you have your actual adapter, you should have your IP address, and it should be a private address typically. Again, NAT is involved so that I can get internet access. But I'll have an FE80 address. And you'll notice even my default gateway is an FE80 address. That's because for IPv6, local communication is done through the link local addresses. So your default gateway, you'll have an IPv6 variation and an IPv4 variation. Even if I had a fully publicly accessible IPv6 address space, they're still going to use the link local, the FE80 type addresses for local communication. So between my device and my router, it will still use FE80. Remember that that router is actually known as the default gateway. It's the machine that is on our network that also can forward packets to another network. And that's a layer 3 device, typically our router. And again, we call that the default gateway. And that's going to be in the same network for our IPv4 and IPv6 address spaces so that they can communicate both locally and can forward our requests to our destination location. Alright, so when we're talking addresses, oftentimes we also know what's called a CIDR, or classless inter-domain routing. Basically, this means this is the size of the network, and we can use it to manipulate what's going on. So for Class A, the default subnet should be a 255.0.0.0. For Class B, it's 255.255.0.0. For Class C, it's 255.255.255.0. And again, these are just the standard subnet masks for the different classful addresses. Well, you can also denote them as a /8. You'll notice the 255.0.0.0, it's 8 bits. 8 bits equals 255. That's the binary to decimal conversions. So, with Class A, it's /8 or 255.0.0.0. For Class B, it's 255.255.0.0. The 255s, again, each make up 8 bits, so that's actually 16 bits. That's why it's a /16. Or we have our Class C. Yes, our Class C is 255.255.255.0, but you'll notice the range of our private addresses are a /16. So this Class C private range is a little bit unique in that it uses a /16, even though we know that typically a Class C network will have a 255.255.255.0. So it should be using a /24, but because it's a private address space, as long as it starts with 192.168, it can be any number, any other numbers. So with that said, these are private address spaces. So with IPv6, we have a automatic private address, and it's that FE80 address. And again, we already know the APIPA address, a automatic private IP address, is also a 169.254 based address. These are both classified as self-generated addresses, meaning if you cannot get an address through either DHCP or through a static assignment, you'd be automatically generated one of these addresses. So we brought up IP static address assignment versus DHCP. So what does that mean? Static assignment is when you manually assign the IP address portions. And again, the address portions are going to be the IP subnet gateway, DNS, and possibly a domain that's associated with those individual devices. So on this diagram, we're talking about DHCP. DHCP is Dynamic Host Control Protocol. It is the protocol in charge of dispensing IP addresses from a pool of addresses that was configured on a DHCP-based server. DHCP works off of broadcasts, a DORA process, a discovery, offer, request, acknowledgement, DORA. And this process is about how individual clients get those addresses. Well, it's a broadcast, meaning it cannot go over a layer 3 network or a layer 3 boundary. Broadcasts can only occur at layer 2. A layer 3 device will typically not forward a broadcast on. We can have what's called a relay agent, and that's normally attached on a router or another layer 3 device that is configured specifically to forward those broadcasts on. The relay agent will receive a broadcast, will look at it and go, oh, this is attached to an appropriate configuration to forward it on. That way, the clients can actually do a broadcast to a remote DHCP server, and as long as there's a relay agent there, the relay agent will be used to relay the broadcast to the DHCP server. The server then will respond to the request using that DORA process and will be allowed to assign an IP address to one of the clients. And again, that's going to happen for every single client that is given an address. There are two main types for address assignments. Again, static and DHCP. DHCP is really great for devices that doesn't matter if the address changes. But for things like a server or a printer, things like that that need to stay static, that need to stay the same IP address, we're going to have that static IP assignment. And that is what allows for a nice combination of a network. So I'm actually going to take my pen and I'm going to draw. So if we then attach a server here, or a printer, these are devices that will have it. Not every device on the network, not all the clients need to be DHCP. Some can be DHCP, some can be static. So you can have a combination network that has both. So I said the four components that DHCP hands out is IP address, subnet, default gateway, DNS, and domain. So the DNS is actually about name resolution. It resolves the host name to an IP address. Typically, it will actually look at the fully qualified domain name, and that identifies a host and the location of the host given a DNS-based scope. www.google.com is a fully qualified domain name. Google.com is not. Google.com may redirect you to www.google.com, but that's a redirect. The shortened name that points to the fully qualified domain name is different. If we're talking a device name or a computer name, it may be pc1.domain.com or something along those lines. That would be the fully qualified domain name for a computer. So here is our IPv4 address configuration screen in a Windows-based computer. You'll notice we have the obtain automatic addressing for both our IP and our DNS. If we wanted to manipulate our addresses, we would use the following address space, and then we could manually type in our addresses. If you wanted to play with the alternate configuration, you can do that, or if you wanted to play with the advanced configuration. You'll notice here DNS you have two options. If you click advanced, you can have more. So in advanced, if you click on DNS, you can add multiple DNS servers. You can also register a domain query or domain name that will be used on your local network in this setting. And that part of that is going to be that default domain suffix or the search domain. You would type it in there, and that would be a local domain. So that could be something like domain.local or company.local. Those typically are not internet-based domains. That's going to be a name of a domain that is used in the Windows environment. I keep saying the word domain, and that is because in the Windows realm, we have centralized management called Active Directory. It's a directory service. Inside Active Directory, directory services, we have the ability, one, we give Active Directory a domain name, something like company.local, and that centralization allows us to centralize objects, users, passwords, resources, and we can also then hand out policies. So here we have acme.com is the domain. All of our devices are connected to that domain in this example. Well, we can have a policy that will be handed out to all computers on that domain. That's called a group policy object. We use the group policy management to actually configure and manage all of our policies. Our policies are basically made up of every single setting that Windows can have, plus more. You can configure local policies, computer-based policies, you can configure user-based policies, you can configure just about everything via a GPO. If you want the Windows machine to start and display a specific background, or add a certain printer, or add certain resources, all of that can be done through a group policy. And again, configuring the group policies is outside the scope of this, but understanding that that policy portion exists is what's important here. Here we have a primary DNS suffix setting, so you can actually set the DNS domain or the DNS suffix through a GPO. And that way, it can be pushed to all of your machines. The nice thing is when you do that, everything has the unique domain associated with all of them. You can centralize those settings so that everyone can be unique, but everyone still has similar settings. So there are other network services, things like WINS and NetBIOS. These are fairly old and aren't as often used anymore, but you can configure under WINS our NetBIOS and our WINS names. So we talked earlier about the transitioning for private IP addresses to a public address, and we said the word NAT. So NAT is Network Address Translation. It allows us to mask a single or multiple private IPs to a single or group of public IPs. Public IPs are what's allowed on the internet. So that's why we can all have a 192.168 address, and we're all still allowed on the internet. That's because those addresses are not really addresses on the internet. Our router has either NAT or PAT set up automatically that will translate all of our private addresses to the public address that our internet service provider, ISP, gives us. We also have other address types other than IP addresses, like a MAC address. And that's a physical address. And you'll notice our MAC address is broken up into two groups, the OUI and the UAA. The OUI is essentially the vendor or manufacturer. If we're talking about configuration, here we have an older server using 2012, but the technology is still there, whether it's server 2012, 2016, 2019, or even 2021 server. The process is called NIC teaming. Essentially, you can take two or more network ports and you can team them together. You can combine them. And this allows for increased bandwidth and a little bit better fault tolerance, because if you have one NIC and you have one adapter, one cable plugged in, if that adapter fails, access to that server goes away. Well, if we have two NICs working together and there's two cables and they're teamed together, they're going to share one IP address because they're teamed together, but if one fails, the other one still functions, so that availability is still there. We also have the ability to configure a network adapter so we can manipulate what resources they have. Are they going to be a gigabit? Assuming that that can handle it. Can it be a 10 gig? If we have multiple adapters and there are multiple speeds, we normally want to use the common speed across all of them. Faster is better, but at the same time, if we have one side operating at 10 gig and one side operating at 1 gig, there will be some issues. In a server realm, or Microsoft server realm, you can actually go to the adapter settings and you can click on Team and you can combine the two adapters. Here we're combining two 10 gig adapters to work as one. And you'll notice we can have them as like one active, one hot, or one active, one a standby. We can have them work together. We can have them independent. So it really just depends on what we want. And when they're done, they will act as one adapter. So earlier we brought up speed. That's going to be if we want to manipulate the speed. Oftentimes it's set to auto-negotiate, and that's good enough. But there are times where one device is hard-coded to 1 speed. It might be a 1 gig port, but you're paying for 100 megabit speed. So it can negotiate at 1 gig, but you're only paying for 100 meg. So if you go over that, they may charge you. So you want to be able to hard code the speed. This is often done in a data center, and that way you have that additional bandwidth if you want, but again, that charge option is possibly there. We also have half duplex and full duplex, and that is what can send and receive. Full duplex, we can both send and receive at the same time, where with half duplex, we can either send or receive, not both at the same time. Ports and protocols, which we've already discussed in length in previous sections, but just in case, protocols are the way that we communicate. Ports are attached to those services that operate with those protocols. The big two are TCP and UDP. Those are transport layer protocols. TCP provides guaranteed service, also known as connection oriented. UDP provides non-guaranteed, best effort, connectionless delivery. TCP has more overhead because it will guarantee the delivery. But when you have something that's real time like voice or video, UDP is better because you don't want to wait for packets to be sent, received, verified, and checked. That's too much delay. So UDP is really great for having any type of real-time based traffic when a guaranteed delivery is not necessary. So we also have what's known as port numbers. So port numbers are essentially the number that the service will operate on. And again, they can be either UDP or TCP. And we have basic protocols like Simple Mail Transfer Protocol uses TCP port 25, or we may have Secure File Transfer Protocol, SSH, and that uses, I believe, TCP port 22. Some protocols might use both UDP and TCP, we just have to check. So you have to keep in mind there are 65,000 ports, and that means 65 plus 1,000 TCP and 65 plus 1,000 UDP. You're not going to remember them all, and that's okay. The goal here is to see the common ports, FTP, SMTP, SSH, NTP or HTTP or HTTPS. Those are common ports that you want to know. NTP does time. HTTP and HTTPS are the web protocols for sending a web connection, a web page. We have things like IMAP and POP. Those are used for receiving email. IMAP is port 143, POP is 110. We have our RDP, or our remote desktop for Microsoft, using port 3389. Those are, again, pretty common test questions. Sally is trying to remotely connect to a Windows machine. She uses port 355. What's wrong? Well, the default port is 3389, so they expect you to at least know that port number. Other things are like the TLS SSL based FTP that might be using port 989 or 990. Those are pretty common when it comes to email as well. Active Directory uses port 389. DNS uses port 53, both TCP and UDP. And DHCP by default uses port 68, both TCP and UDP. So that covers our protocol portion, but that's not it for this section. Remember we said that we're going to talk about cabling. So here is a pretty common cable. This is a Ethernet cable known as unshielded twisted pair. It's called unshielded twisted pair because there are 4 pairs of twisted cables that are separate. You're going to notice they're unshielded, meaning they're not individually shielded. That's pretty common. But each section are colored. And I don't know why this diagram has them colored really weirdly, but normally they are orange, one orange white, blue, one blue white, green, one green white, and brown, one brown, and one brown white. They make up the 4 pairs of an Ethernet cable. When we are making a cable, we follow the CIDR standard T568A or 568B. Normally, T568B is the most common. And I said the color code, and in the photo you should notice that the adapter, the head of the cable, follows a very specific pattern. Orange, orange, green, white, blue, blue, white, green, white, brown, brown. And that's a pretty color standard for an Ethernet cable. So a straight through is when we have the same color pattern on both sides, and that connects almost all devices. If you want to get very specific, if you're connecting 2 like devices, you need to have a crossover cable, and that is where you have CIDR 5 or 568A on one side and 568B on the other side. It rolls over pins 1, 2, 3, and 6. That way, the sending and receiving pairs are swapped. And again, crossover are for like devices, and a straight through is used for everything else. A third cable type is known as a rollover. And a rollover is literally all of the pins just flipped. So pin 1 goes to pin 8, pin 2 goes to pin 7, and so forth. All of the pins are flopped. And this is normally used for configuring devices. You also notice it says it reverses the wiring patterns used to connect a router, switch, or access point. This is about being able to configure them. Not connect to them, but configure them. We have Ethernet cable. They are typically called a CAT cable. CAT 5e, CAT 6, CAT 7, CAT 8. CAT 5e and 6 are the more common ones used today. CAT 6 is easily probably taking over most wiring now. If you go to the store like Best Buy to purchase a cable, you're probably going to be buying a CAT 6 cable. Might be a CAT 6A cable, but it will still be a CAT 6 cable. And they can go 100 plus meters, and they operate up to speeds of up to 10 gigabits per second. But again, you have to have a receiving and sending device, a computer, a network adapter, and a switch that can operate at that 10 gig speed. We also have our fiber connection. Our fiber is based off of different types of connectors, an ST, an SC, an LC, or those are 3 of like 8 different types. These types of connectors are not the only connectors out there. And again, these comes as pairs. They're not individual. LC will have 2. SC will have 2. ST will have 2. They always come in pairs. One for sending, one for receiving. And there are different speeds. Some can go 40 kilometers, some can go, 5 kilometers. It really just depends on the fiber itself. The fiber itself also has adapter cards. So when you plug the adapter into a switch, for example, you get a SFP connector, a small form factor pluggable adapter. Basically, this is an agreed upon interface that devices can use for us to be able to configure. Here we see a LC, like this is an LC adapter. It's plugged in using orange fiber. Well, this adapter is being plugged into a module for a Cisco switch or an HP switch. On the adapter side, we're going to have a network adapter that has a similar type interface that you'd plug the SFP into. Here is a very hazy photo of a RJ11, a traditional phone cable, and an RJ45. So this is an RJ45. Again, that's 4 pairs, 8 cables. An RJ11 is 3 pairs or 6 cables. This is used for data. This is used for phone. So as we're talking about cabling, we also have to worry about cable management. You can't just put a cable on the floor and expect them to survive. We have what's called a raceway. This is a cable protector. That way people don't trip over or run over the cable and the cable gets damaged. This could also be a cable organizer. This can separate the different components of the cable. We have cable management trays for horizontal, going overhead, for example, in a false ceiling. Or if we have to climb a wall or something, we have vertical management trays. That way our cables can be kept organized. So how do we organize things? We do that with labels. Labels are one of the big ones. Normally we will label the cable, the ports, the systems, the patch panels, the termination portions. We want to label the cable so we know where they're going to and where they're coming from. That's one aspect of it. We also have to be able to organize the cables using cable ties. That way the cables are all kind of grouped together and we don't have to worry about them going away. We don't have to worry about them getting loose. So that's all we had for this section. If you have any questions or concerns, definitely feel free to reach out. Thank you. So I want to thank you for going through this video lecture. If you have any questions, any concerns, definitely feel free to reach out. Remember that it's not enough just to go through the video lecture. You want to make sure that you're understanding the material, and we do that by asking questions. So however we have the medium set up for questions, ask them, reach out. Let's discuss some of the topics in the chapter so we can further our understanding of what's going on. I look forward to working with you throughout the remaining of the modules. Thank you.